Hello friends, welcome back to my channel Chemistry Unplugged. So today we will take Tanabe Sugano diagram. These diagrams are used, these are the correlation diagrams for coordination complexes. So I will tell you what is the concept of these diagrams with examples, and we will also discuss sprint crossover. We will take some questions from CSIR net based on this topic, and you can follow me on Unacademy using my name or this link. And please subscribe to my channel. So let's start the video. First we will take some important point about these diagrams, then we will move on to the diagrams, how we can draw them. So first point is TS diagrams. TS is the short form of Tanabe Sugano diagrams. Okay, so I will write TS. TS diagrams are used for both high and low spin complexes. Okay, octahedral complexes especially, because tetrahedral complexes are always higher spin complexes, and in case of octahedral complexes, if we orbital diagrams, we can draw them only for high spin complexes, but TS diagram can be drawn for high as well as low spin complexes. Then terms of different multiplicities are also included. In case of orbital diagram, we only included low, or you can say ground state multiplicity terms, or high multiplicity terms. But in case of TS diagrams, we will include all the multiplicity terms for a particular electronic configuration. Next is ground state term is taken as reference term. What is the meaning of this? Suppose we have a orbital diagram for D for 2D. Then in this case, we draw it like this. This splits into two, T2G and 2EG. It splits like this, and we can, on this axis we take energy, and on this axis we take ligand field strength. Okay, and from this we can identify the number of absorption electronic transitions taking places. So in these diagrams, we take our ground state term like at this position, and then we split into 2 or 3, okay, according to the term. For example, D splits into 2, T2G and EG. F splits into 3, A2G, EG and A2G, T1G and T2G. But in case of Tanabe Sugano diagram, we take ground state term as reference, means we will take it as at 0. This is the energy axis and this is ligand field strength. So we will take ground state term as reference at 0 point. So 2D will be placed at this position, and when it splits, when the ion form a complex, then it will split into 2 terms. So T2G will be on x-axis and EG will move upward like this. So this is the way of splitting in case of TS diagram. This is the basic difference between orbital and Tanabe Sugano diagrams. Then on x-axis we take ligand field strength in terms of del naught for octahedral complexes. So we will not represent it by simply del naught. We will take a new term, del naught upon B. Similarly, on y-axis we are not taking E, we are taking E upon B, where B is Raka parameter, which denotes which is a measure of repulsion between terms of same multiplicity. So here I have written that ground state term is taken as reference. So how you will identify ground state term? You know that ground state term is calculated using the Hund's rule, following Hund's rule. First, filling the electron. If you are filling the electrons following Hund's rule, then this term will give you this. The filling will give you ground state term. And if you have 3 or 4 terms and you have to identify which term will be your ground state term, then how you will identify? Suppose you have 3F, 3P, 1G, and suppose you have 2I. Then how you will identify what will be your ground state term? So first rule is, when multiplicity is highest for a ground state term, the multiplicity should be highest, means the term which has lowest energy has highest multiplicity. So among these four, these two have higher multiplicity, and in these two, which will be your ground state term, which has higher value of, okay, so F has higher value of D, so this will become your ground state term. Then we will take some more important points about this. The fourth point is, one TS diagram can be drawn for different isoelectronic system. Means suppose you have aqua complex of vanadium, in which vanadium is in 3+ state, and you have, so these two complexes are isoelectronic complexes because in both cases we have D2 electronic configuration. So TS diagram will be same, but the value of B will be different. Okay, the pattern of splitting will be same, but the value of B will be, Raka parameter will be different. B and other Raka parameters like C defines the, C is the measure of repulsion between terms of different multiplicities. B is the measure of repulsion between terms of same multiplicity. C is the measure of repulsion between terms of different multiplicities. Okay. Then we will take next point. Electronic transition takes place between terms of same multiplicities. Okay, we always transition takes place between terms of same multiplicities. Suppose we have 3T1G as our ground state term, and higher energy terms are 3T2G and 2EG. Suppose these are two terms. Then transition can take place from this to this, but not this one, because their multiplicities are different. So this type of transition is not allowed. We will say it later in more detail. Then non-crossing over rule. Non-crossing rule means term of same multiplicities, terms of same type cannot cross each other. Okay, so two T terms, suppose we have two T terms, so they cannot cross each other. They will show somewhat repulsion. Their shape will be like this, banded shape, like this. Okay, so there is repulsion between them. They will not cross each other. So this is the rule we have studied in orbital diagram also. So this rule is same. Then we will take that. Okay, one thing to remember is D10 minus N HSOH is equals to DN TD. What is the meaning of this? D10N means it denotes that the number of electron in D orbital. If you have suppose D3 electronic configuration and it is your suppose high spin complex in octahedral, so its pattern will be similar to 10 minus 3 is D7 tetrahedral. Okay, similarly for D8 high spin octahedral complex, so for D8 high spin octahedral complexes, the pattern will be similar to D2 tetrahedral. So in this way we can identify that which octahedral complex, high spin octahedral complex pattern will be similar to which tetrahedral complex. So next is D2 and D7 electronic configuration or have almost similar type of splitting, or this is for octahedral complexes. And if we compare them with tetrahedral complexes, this will be equal to D8 and D3 tetrahedral complexes. So here we will take D2 first. So for D2 electronic configuration, we can fill electron like this. This is your T2G and this is EG. So the value of L for this one is 2. This is plus 2 plus 1, 0, minus 1, minus 2. So this is plus 2 and plus 1. This is 3 and S value is 1. So the multiplicity value is 2S plus 1. So it will become 3. Multiplicity will become 3. So the term will be, ground state term will be 3F. In same fashion, you can calculate other term symbols. We have discussed about how to calculate term symbols in previous videos. So you can watch there. The different terms for D2 electronic configurations are 1D, 3P, 1G and 1S. So as I have told you earlier that in case of TS diagram, we will consider other terms also. In case of orbital diagram, we consider terms of only same multiplicity. We have considered only 3F and 3P. But in case of Tanabe Sugano diagram, we will consider all the different terms, including all type of multiplicities. So suppose this is our graph and we have to place these terms according to their energy, because this axis is for energy, E over B here, and we have here del naught over B. So we will place these terms according to their energy. So in case of free ion, these terms will be here, they will not show splitting. So we have here the ground state term 3F, then next term is in energy level is 1D, then we have 3P and then 1G and 1S is highest in energy level. So in this way we place all the terms, and when this free ion will form complex, these terms will split. Suppose F splits into 3 terms, A2G, EG, T2G. D splits into EG and T2G. P does not split, but energy level is increased and it will become different terms T1G. Then G also splits into 3 terms, T1G, T2G, EG and A1G. And S does not show splitting, but its energy increases and it will become A1G. So in this way all the terms show splitting, and in this way this graph will become highly complex in nature. So we will not consider the complex diagram for our study. We will consider only the terms of higher multiplicities of same type, 3F and 3P. So in this way, Tanabe Sugano diagram will become similar to the orbital diagram, but only the difference is the axes are different and how we can use these diagrams, the way is different, but the pattern will become same after excluding these types of terms. We will also take complex, but first we will consider the simplified form of the TS diagram. So this is the graph for your D2 electronic configuration of octahedral complexes. You can also use this graph for D7 high spin complexes and for D8 and D3 tetrahedral complexes. So you can use this graph for 4 different type of complexes, but you have to consider that what is the multiplicity of the terms used in case of D7. The multiplicity will change. We will see it later in the complex TS diagram of D7. We will take it in more detail. Then D8 and then for D8 and D3, the term will not include Garrod function. G will be excluded, but the pattern will be same. So here in this graph, we have plotted on x-axis, we have ligand field strength in terms of del naught over B. B is Raka parameter, we know this. And on y-axis, we have energy over B. And At 0 axis, we have taken our ground state term, that is 3F, and in free ion, in case of free ion, these all terms are here. They will not show any type of splitting. So their energy levels are like this: 3F, 1D, 3P, 1G, and 1S. So these are their energy levels. And in this diagram, this is simplified form, so we have considered only 3P and 3F splitting. We have not included 1D and 1G and also 1S. We have not included them. So in case of 3F, when ligand field strength is small, suppose at this point, the ligand field strength is small and the terms split it into 3T1G, the ground state term split it into 3F will split into T1G, T2G and A2G, and the lowest term T1G will form the axis, ground axis, x-axis. Okay, it will be placed like this. I have denoted it by orange line, so you can see this. This is your T1G and this one is T2G and this is A2G. Okay, and as you increase the value of ligand field strength, as you are moving from weak field ligand to strong field ligand, the pattern of splitting increases. Okay, and the P also shows split. It is not splitted, but its energy increases as we increase the ligand field strength, and it is denoted by 3T1G, and we have placed P in the bracket to differentiate it from the F terms. Okay, and this energy gap between these T1G and T2G is 15B. This is given in the box that this energy gap is 15B, and it remains almost constant as you are moving from weak field to higher field strength. Okay, this gap is almost constant. Then how we can use this diagram? Suppose we are taking weak field complex. Suppose we have example here. So first we are taking cobalt complex and it is in +2 state. Okay, so this is for cobalt. The field is weak field strength. It is low field. It is the ligand field strength is low. We get transitions. Electronic transitions are from, this is first electronic transition. This one is your second from T1G to A2G, and this will become your third electronic transition, T1G to T1GP. Okay, so your different transitions are T1G to T2G. This is your lowest electronic transition. We will denote it by nu1. Second transition is from T1G to A2G, and your third transition is T1G to T1GP. So these transitions are the transitions for cobalt +2, and these transitions lies here in case of cobalt +2 complex. And if we are taking another complex, suppose we have complex of vanadium, this is in +3 state, and the transition of vanadium complex lies in this range at this point. So you have three transitions again from T1G to T2G, first transition. Second transition from T1G ground state to T1GP, and third transition is from T1G to A2G. So your lowest energy transition for vanadium +3 will be T1G to T2G. The second transition will be T1G to T1G, P, this is from F. And your highest transition will be T1G to A2G. So this is the basic difference between the weak field complex and high field complex. So in case of cobalt plus 2 complex, which lies in weak field, the transitions are, first highest transitions are same, but the second highest transition is different. It is in case of cobalt plus 2, it is from 3T1G to 3A2G, and in case of vanadium plus 3, it is 3T1G to 3T1GP. So this is the basic difference. Next thing is how we can use these diagrams. These diagrams can be used to calculate del naught value and B. So how we will calculate it? We should have information about the UV spectrum of complexes. Okay, so in case of suppose vanadium plus 3, this transition lies around 17,200 centimeter inverse. This one lies nearly 25,600 centimeter inverse. And this third band is this third band is of very weak intensity, but it lies nearly 36,000 centimeter inverse. So suppose this one is E1 energy and this one of E2 energy and this is of E3 energy. So the ratio of E1, we can write it like this: E1 upon B, E2 upon B will be equal to, or you can write E2 upon B and E1 upon B equal to 25,600 upon 17,200, and this value is nearly 1.5, and it means the ratio of energies E2 E1 is nearly 1.5. So if you want to find out in the graph that at which value of del naught the ratio of two energy gap, this is the gap from this point to this point is your E1, and the gap from this point or to this point is from this complete gap is your E2. So this ratio, the ratio of E2 upon E1 should be 1.5, and at the value of 28 delta naught upon B, this ratio is equal to 1.5. At this point of graph, where I have denoted it by this dashed line, the ratio of E2 upon E1 is equal to 1.5. If you calculate this ratio at this point, you will not get the value of 1.5. So at the value of delta naught upon B equal to 28, this ratio is equal to 1.5. It means, and now we know the point at which this ratio is equal to 1.5. So we can identify the value of E1 using the y-axis, and if we try to find out the value of E1, we will draw a line like this which matches this point. I have not drawn it correctly, but it should match this point, and the value of E at this point will be equal to E1 upon B, and this value is equal to E1 upon B from this graph is 26. Okay, and the value of E1 is 17,200 upon B equal to, we can place the value of E1 here, so it will become 17,200 upon B equal to 26. From this we can calculate the value of B. It comes nearly 660 centimeter inverse. So now we can calculate the value of del naught. Del naught upon B is equal to 28 at this point. So del naught will become equal to 28 into 660. It is nearly equal to 18,500 centimeter inverse. So in this way, we can calculate the value of Raka parameter and del naught using these diagrams. Similarly, we can calculate the value of del naught and B for cobalt complex. If we have the UV spectrum of this complex, we can identify the value of E1 and E2 and E3, and using any of these two ratios, E1 upon E2 or E2 upon E3 or E3 upon E1, we can identify the value of B and del naught. Next we will take the graph for, this is the graph for D3 system, D3 octahedral complex. We can also use this graph for D8 octahedral complex. I will not write here high spin or low spin because in case of D8 the pattern will be same. Okay, and we can also use this graph for D7 and D2 tetrahedral complexes. So in this graph again we have plotted delta naught upon V on x-axis and E upon V on y-axis. The ground state term for this is 4F and this another term of same multiplicity is 4P. There are many other terms also, but we have not included them. Otherwise this graph will become very complicated and we only need these terms to calculate for our studies. Okay, so in case of this diagram, 4F will split into 3. Okay, we know that F will split into 3 terms. But in case of D3, A to G will become ground state term. We know that how we can identify that A to G will become ground state term or T1G will become ground state term. You can, if you have not understand it, you can see my videos on orbital energy diagram. I will tell you a little bit here, that is, if in case of D3 you are filling electrons like this, all the three electrons will go in T2G. So in this case this state is non-degenerate. You can fill electron only by single way. You cannot fill electrons in multiple ways. So this state is called as non-degenerate state. That is why we use a term A for, so that is why we are using a term A to denote this energy level. So in case of 4F D3 system, the ground state will become 4A2G and T2G will go like this, and then third one is 4T1G. Now we have second state with same multiplicity is 4P, and it will rise in energy level as we are increasing the ligand field strength, and it is 4T1GP. So according to the non-crossing rule, these two terms, because they are of same type, T1G and T1G, so they will not cross each other, they will repel each other. So that this diagram is little bit curved in nature because they cannot cross each other. There is repulsion between these two terms. So in this graph I have drawn 3 dashed lines. What is the meaning of these lines? We are taking here 3 complexes. We have one tetrahedral complex. Suppose we have CuCl4 2 minus, and next we have nickel plus 2 complex. This is aqua complex of nickel, and third one is chromium plus 2 complex. This is also aqua complex of chromium. So these 3 lines denotes the value of del naught over V, for which we get the ratio of E1 and E2. As we have done in the previous example, we can do similarly. Because tetrahedral complexes of cobalt are the weak field ligand, so they are close to this axis. They have very weak field strength. So they lies here. And from this value we can calculate, from this value of delta upon B, we can calculate the value of del naught and B. Okay, if we have the value of this, suppose this is E1 and this is E2. So if we have the values of electronic spectrum from which we can get the value of E1 and E2, and we have a fixed ratio. Suppose E1 upon E2 for cobalt complex is, this is suppose 1.2. Okay, so you have two values of E1 and E2, and from, if you divide these two values you will get the value 1.2. okay, and from this value you can identify at which value of delta B upon delta naught upon B you will get the ratio of E1 upon E2 equal to 1.2 in this graph. Suppose at this point the value of E2 is, suppose this is E2 upon E1 ratio, this is E2 upon E1 ratio. So at this point the value of E2 is suppose 8. Okay, and the E1 value at this point is suppose, this E1 value is suppose 6.7. So at this particular value, at this particular range, you will get the perfect ratio of 1.2. So you can draw a line at this point and you get the value of delta naught upon B. Suppose it is nearly 4. So at this value, you can calculate the value of delta naught and B using the electronic spectra and this graph. Similarly, you can calculate the value of delta naught and B for nickel and chromium complexes, because these are high field ligand, these are high field complexes, so they will shift towards right hand side because there is increase in the value of delta naught upon B. Next we will take the complex TS diagram of D7 electronic configuration. We have seen in case of this diagram, this is the graph, this is the diagram for D2 and D7 high spin. This is only for high spin. But as I have told you that TS diagram can be used for high spin as well as low spin complexes. So in case of D7, how we can use TS diagram in case of low spin complexes? So this is for low spin complexes. This graph is divided into two parts by this red line. This is this area for high spin region and this is for low spin. Okay. Then on x-axis we have again draw delta naught upon B, and y-axis we have energy over B. D7 electronic configuration can have different terms: 4F, 4P, 2G, 2F. Okay, but we are using here 4F, 4P and 2G only. Okay, if we will use 2F also, then this diagram will become more complex. So we are including only 4F, 4P and 2G. In case of high spin complex, we have already seen in case of D7 high spin complexes, we have considered only 4F and 4P. We have not included 2G because in case of high spin region, the 2G is of not use. But in case of low spin complexes, 2G will participate. Then how it will participate? Let's see. So 4F will split. This is the region at this point. This is for free ion, where these terms are not splitted. But as we are increasing field strength, these terms will start to split. And this 4F, this F term will split into 3, T1G, T2G and A2G. Okay, so because here we have weak field, the ligand field strength is weak, that is why it will form high spin complex. So for this area we have these type of splitting of T1G, T2G and A2G. So first we will see this part, left hand side of the diagram. So 4T1G is on x-axis, then 4T2G will rise in energy level and A2G will be of highest energy. Similarly, 4P will rise in energy and it will be denoted by 4T1GP. Okay, so this pattern is similar to the previous one. Okay. Now, if we want to find out electronic transition in case of weak field complexes, we can identify if the field strength is very weak, then this one become your E1, this is your E2, and this is your E3 transition. And if you are increasing field strength a little bit more, but the complex is still high spin complex, then your first transition E1 will be from T1G to T2G, second will be from T1G to T1GP. Okay, so this is the difference between weak field and high field. In case of weak field, second transition is from T1G to A2G. But in case of high field strength, the second transition will be from T1G to T1GP. And third transition will be T1G to T2G. Okay, next important thing is the electronic transition will be between terms of same multiplicity. We have studied about it in the important points that electronic transition will be between terms of same multiplicity. That is why I am considering only 4 terms with 4 multiplicity. We have not included the terms of G. The G is also splitted, but it has different multiplicity. Okay, it is splitted, G term is splitted into E, 2EG, this is EG. And this one is T1G, 2E1G. This second dashed line is 2T2G. And this one is 2A1G. So G term is also splitted. As we are increasing field strength, G term will also show splitting. But we are denoting it by dashed lines because here we have the ground state term with multiplicity 4. And the electronic transition takes place from ground state. So we will not consider these terms of different multiplicities for electronic transition. Okay. And this red dashed line will show your spin crossover point. This is the field strength at which your complexes will show spin crossover. High spin complexes will become low spin complexes. So now comes the role of 2G. As you are increasing the field strength further after 20 value, the EG term, this is your EG term, it is at this point. This will become your ground state term. And T1G term, this is T1G term of 4F will rise in energy. Similarly, these all terms will also show rise in energy level. All the terms will show. Only E1G will become your ground state term. Now your ground state term has a multiplicity value 2. Okay, and the terms of 4F have multiplicity 4. So we cannot consider these terms for electronic transition because our ground state term has multiplicity value 2. So electronic transition will take place from ground state. So we cannot consider these terms. That is why I have denoted them by dashed lines. Now we will not consider them in case of low spin complexes. And the terms of G, all the terms has multiplicity value 2. So we will consider them in electronic transition. So electronic transition will take place from 2EG to different terms of spin multiplicity value with Okay, so this is the difference between high spin and low spin complexes. So in this way, you can identify that how electronic transition will take place in high spin and low spin complexes. And second important thing is this type of graphs, these type of diagrams in which the graph is split into two parts, high spin and low spin complexes, can be possible from D4 to D7 electronic configuration, because the reason is very simple. Because in case of D3, all the electrons will go in T2G. Okay, there is no chance you can form high or low spin complex. But as you increase one more electron, the electronic configuration will become D4. Then you can differentiate low spin and high spin complexes. All the electrons can go in T2G, or in case of low spin complexes, and for high spin complexes they can go in EG. Similarly, in case of D5, D6 and D7. Once you get D8 electronic configuration, then there is no difference between high and low spin complexes. So this is all about D7 electronic configuration. Then we will take what is the meaning of spin crossover. Spin crossover will be shown by D4, D5, D6 and D7 electronic configurations, because in that case we have two parts of this graph, high spin and low spin, and at this point the graph can show switch from high spin value to low spin value. So only if D4, D5 and D6 electron complexes with these configurations can show spin crossover. Then second thing is octahedral complexes can show spin crossover, because tetrahedral complexes are always weak field complexes and they form always high spin complexes. That is why they will not show spin crossover, because all the complexes are of high spin. So if ligand lies in the middle of a spectrochemical series, then you can see spin crossover, because these ligands can have characteristics to form high as well as low spin complexes. So in that case you can see spin crossover. Spin crossovers can be seen in 3D complexes only. You cannot see this effect in 4D and 5D complexes, because 4D and 5D complexes always form low spin complexes. Okay, they will always form low spin complexes. So in that case you will not see this effect. Fifth is presence of mixed field ligand. If you have two ligands, suppose you have phenanthroline and you have water, these two ligands are present in a complex, then these type of complexes can show spin crossover, because phenanthroline is high field. This phenanthroline is a strong field ligand and water is weak field ligand. So these type of complexes can show spin crossover. Then mostly seen in iron and cobalt complexes. This type of effect mostly seen in iron and cobalt complexes. 7th point is temperature, pressure and external magnetic field can cause spin crossover. If you are increasing or decreasing temperature, pressure and external magnetic field, then you can see this type of effect. For example, if you are increasing temperature, if temperature is high, then complex will be of high spin, and for low temperature conditions complex will be of low spin. So always remember this: for high spin, high temperature, high spin; low temperature, low spin. So we will take an example for this also. And next we have a question from CSIR net. The question is: choose the correct statement about Tanabe Sugano diagrams. A point is E upon B is plotted against delta naught upon B. This is right statement. We know that delta naught upon B is on x-axis and E upon B on y-axis. Second point is the zero energy is taken as that of the lowest energy term. This is also right, because the lowest energy term is placed on x-axis on 0 energy level. So this is also a correct statement. The next is terms of same symmetry cross each other. This is not correct. We have seen that in non-crossing rule, the two terms of same symmetry cannot cross each other. So this is a wrong statement. This one is wrong. These two are right. Then fourth statement is two terms of same symmetry bend apart on increase of ligand field strength. This is the correct statement. The terms will bend apart like this. So this is the correct statement. So statement A, B, D are correct. So the correct option should be option 3. Okay. Next we have a question from June 2017. The question is mu effective of this complex of iron changes with temperature with the involvement of two electronic states. The states are low spin, high spin complexes with different terms. So in case of orbital diagram, this is not possible that you can see the effect of temperature from low spin and high spin complexes, because in case of orbital diagram we considered only high spin complexes. So this is only possible in case of Tanabe Sugano diagrams. And I have told you that in case of spin crossover, the effect of, what is the effect of temperature? If you are increasing temperature, the value of spin will change. For high temperature, we have high spin complexes, and for low temperature, we have low spin complexes. And if we have high spin, the value of mu will be different, because we have different number of lone pair of electrons. We have different unpaired electrons. So we have the complex of iron, and this ligand has negative charge, one negative charge. So iron has +3 state. So for +3 state we have D5 electronic configuration, because iron is in D6, 3D6, 4s2, and after removing 2 electrons it will become D5. Okay, because iron is 26. So this is D5. D5 means, suppose we have two different types of complexes. We will take high spin as well as low spin complexes, because in spin crossover, with the increase of temperature there is change in the spin of electrons. So we will consider high spin and low spin complexes. So if we have D5 with high spin, we can fill electron like this. And if we have low spin, we can fill electron like this. So in this case, this state is not degenerate state, because we can fill electron by only single possible way. So it should be denoted by A. Okay, and if we calculate the value of multiplicity, all the electrons are unpaired. So the value will be 1/2 plus 1/2 plus 1/2 plus 1/2 plus 1/2. 5 is multiplied by 1/2, and multiplicity will become 2 into 5/2 plus 1. So this will become 6. So this term has 6A, high spin complex. And for low spin, we have, this state is triply degenerate, because this T2G has dxy, dyz and dz orbitals. So we can fill these electron by 3 possible ways. We can fill them dxy, yz, zx, 2, 2, 1. Or we can fill them like this, dxy2, dyz1 and dzx2. And one other possible way, dxy1, dyz2 and dzx2. So we can fill these 5 electrons in 3 possible ways. So this state is triply degenerate. So we will use the term T for this. And because we are considering x, y, y, z, these orbitals, so this will become T2g. Okay, and if you calculate the multiplicity, then it will comes out as 1 by 2 minus 1 by 2 plus 1 by 2 minus 1 by 2. So we have only 1 by 2. So 1 by 2 plus 1 is equal to 2. So this is 2T. So the answer, the option is from low spin 2T2G. This is low spin and 2T2G, and high spin this 6A1G. This is 6A1G. So the option first will be the right answer. So this is all about Tanabe Sugano diagram. Thank you so much for watching my videos. Please like, share and subscribe to my channel and press the bell icon for future notifications. Thank you so much for watching.